All right. Yesterday, we talked about this formula here. Cosine of 2 theta equals 1 minus 2 sine squared theta. It's a double angle. It's one variation of the double angle formula for cosine. And what that does is it allows us, if I want to find the cosine of 60 degrees, or whatever angle, okay, it doesn't matter, just using 60 because it's easy to cut in half. If I want to find the cosine of 60, in order to find that, all I need to know is the sine information for 30 degrees. Does that make sense? Okay. This formula was found through the use of our sum and difference formulas for cosine. Okay. We're going to use this formula to come up with what we call our half angle formulas. So if you play that transitive game, well, the half angle formulas comes from a double angle formula, but the double angle formula comes from the sum and difference formulas. Then we realize that we have a collection of about 9 formulas that all come from the same thing. Does that make sense? Okay. And if we get really good, and I know that it's the first time seeing this, so we're first time trig students, but if we spend a lot of time with this stuff, then we don't need to memorize a series of 30, 40 formulas in trig. We can learn where they come from, and then when we need those other 10, 20, 30 formulas, we can generate them. Okay, and I think that's the way that mathematics is intended in comparison to just trying to memorize things. Okay. Now, we're going to use this to come up with the half angle formula for cosine, and we're going to exploit a relationship that's occurring right now between these two things. There is a 2-to-1 relationship between those two things, right? Okay. We're going to exploit that because if it's a 2-to-1 relationship from left to right, it's a 1-to-2 relationship from right to left. Does that make sense? So I'm going to state here, and this is perfectly fine to do. We're just going to redefine some terms. We're going to let theta equal u over 2, where u is just another angle. Okay? Some textbooks you see them call it alpha, some call it they call theta capital A, and then let theta be replaced with lowercase a over 2 or alpha over 2. But it doesn't matter what variables you use. But it is important to know that this u is going to be an angle measurement. Okay? Well, if I do that, then doesn't 2 theta become u over 2? Or sorry, I'm going to mess that up. 2 theta becomes u. Does that make sense? Okay. So if I go cosine 2 theta now is actually u. So I'm going to say cosine u equals 1 minus 2 sine squared of theta over 2. Sorry. U over 2. Keep getting my thetas and u's mixed up. But theta, right there, replace it with u over 2. Do the multiplication, it becomes u. Okay? Replace this theta with the redefined u over 2, and it becomes that. Is that okay with everybody? Is this still a 2-to-1 relationship like it was up here? Yeah. So this is nothing new. It's just redefining our variables, essentially. Let's solve this for sine now. Okay. If I solve this for sine, I'm going to have cosine u minus 1 equals negative 2 sine squared of u over 2, right? Divide by negative 2. So it's going to go negative cosine u plus 1 over 2 equals sine squared of u over 2, correct? Square root both sides. And I'm going to move sine over here. So square root both sides, so it gives me sine of u over 2. We introduced the square root, so it's plus or minus. Okay, now I'm going to use commutative property and rewrite this as 1 minus cosine of u all over 2. That is our what we call our half angle formula, because now it's the sine half angle formula, because that's what's isolated, right? The sine of u over 2. Okay. What that allows us to do, and I like writing it this way, because now if I ask you, let's say that we're interested in the sine of 22.5 degrees. Or if we're in radians, that's pi over 8. Okay. Well, how can I rewrite that as u over 2? Well, that would mean, how can I rewrite 22.5 so I have the denominator of 2? Wouldn't it be 45 over 2? Okay. And this thing here, and if we go through the formula and look at the comparison here, that u right there is the u that becomes the argument of the cosine on the inside. So in our particular problem, that 45 is u. So we're going to rewrite this, and we're going to apply the formula, and we get 1 minus the cosine of 45 now, all over 2. Well, what's the cosine of 45? Radical 2 over 2. And that's all over 2. Now that's a nasty looking radical. Okay, we're going to clean that up a little bit. Common denominator in the numerator here, if I just look at that, what is the common denominator there? Would be 2, right? Okay, so I'm going to rewrite that as plus or minus. Okay, so it's going to be 2 minus root 2 all over 2. That's going to be just that blue thing, right? Still all divided by 2. Okay, well that 2 is 2 over 1. Can I multiply by that reciprocal? And that's going to give me then plus or minus the square root of 2 minus root 2 over 4. But that's a fraction underneath a radical. So that tells us we can do this, plus or minus 2 minus root 2 all over root 4. But what's root 4? 2. And then a lot of times you'll see, like especially on WebAssign, if there's feedback, they'll actually bring this 2 out as a 1/2 multiplier of that. And that is the best way to write that thing. Okay. Now we have a nested radical there. We have the radical or square root of 2 minus radical 2. Okay, or the quantity 2 minus radical 2. You cannot simplify that any further. If it were purely products underneath that radical, then you could take the square root of a square root, which turns into a 4th root. But we can't do that here because it's a difference. Okay, so you just leave it as the square root of 2 minus the square root of 2. Let's see if that makes sense to us. Let's take our unit circle here. And what I've done on this unit circle is simply put in an angle that is 22.5 degrees. Okay, so that angle right there of 22.5 degrees, when I extend the radius, it creates point B prime, right? So we just found the sine for 22.5, which would be the what coordinate for B prime? It'd be that y coordinate. Okay? So what I'm going to do, I'm going to type in y equals. Now, when we introduced the square root, it became plus or minus. But if B prime is in the first quadrant, it's going to be the positive version of that thing, right? Okay? The plus or minus basically tells me, well, if it's minus, then it's going to be the reflection of B prime down here in the 4th quadrant. or it could be the reflection of the fourth quadrant into the third quadrant. So those are your two negative increments. So it'd be a negative 45 or negative 22.5 degrees, and then if we looked at this one over here, it'd be what, 202.5. So the y values are the same because of the symmetry, but positive or negative based on the quadrant they're in. So I'm going to type in 0.5, and then the square root of 2 minus the square root of 2, and you see that that goes straight through, that y value goes straight through b prime, right? Okay, so that is the exact value for that y coordinate, which you were seeing as a decimal for b prime as 0.3827. Okay, but we now have the ability, and that's what, if I would type in sine of 22.5 on my calculator, it's going to spit back 0.3827. But now with the half angle formula, we can actually have the exact value. Does that make sense? Okay, so what are we doing here? Just like what we did with the double angle formulas and the sum and difference formulas, we can now go, we started with the unit circle having, I think, 17 points on it. The sum and difference allowed you to find the 15-degree increments. Okay, so you could say 15-degree multiples all the way around the unit circle, and you can fit those ordered pairs in as exact values now. What this allows you to do is go in and say, okay, well, I could take the 22.5-degree multiples or the pi over 8 multiples all the way around the unit circle, and I can fill those ordered pairs in with exact values. Does that make sense? So it's just creating a more complete unit circle with exact values. Okay. I'm not going to ask you to memorize those. I don't know those because we don't use 22.5 degrees enough. We don't use pi over 8 enough. But what this allows us to do, if on the rare chance that they show up, you have the ability now to find them as exact values. So that's the way that we find the sine half angle. Let's see if we can figure out what the cosine half angle looks like. And it's the exact same approach to get the formula. But we were looking for the sine in the last one, so we had to use the cosine double angle. We're still going to exploit that relationship. The last one, because I was trying to solve for a sine of the half angle, I needed to use one of the three cosine double angle formulas that incorporated cosine and sine. Okay? Well, now I'm trying to find the cosine half angle. So I need to use one of the three equations or formulas for cosine double angle that uses cosine. So we're going to use this one. That's an alternative variation of our cosine double angle. And just as before, we're going to say let theta equal u over 2. Then 2 theta ends up being u, right? I can replace that with u. And I can replace that then with u over 2. Subtract 1. Can you now solve for that object? Add 1 to both sides, so we get cosine of u plus 1 equals 2 cosine squared u over 2. Divide both sides by 2, right? Go ahead and do that. Now what can I do to both sides? Square root, right? Take square root of both sides, and we get that. And I'm going to go plus or minus. And the plus or minus just, it depends on what quadrant we're in. Okay? Now, if I'm in the first or fourth quadrant, I'm going to choose the positive. If I'm in the second or third quadrant, we'll choose the negative. Is that all right? Okay. So if I want if we want cosine of 22.5 now, that's the same thing as the cosine of 45 over 2. So the 45 ends up being the u in our formula. because 22.5 we know is going to be the first quadrant, I'm going to choose the plus sign here. But then I go cosine of u, which is radical 2 over 2, plus 1, all over 2. That ends up being, common denominator, be radical 2 plus 2 all over 2 from that thing there. And then it's all over 2 again with that denominator there. Multiply by the reciprocal of that, and it's going to give you radical 2 plus 2 over 4. What can I do with that 4? Take square root of it, becomes a 2 on the bottom, and I can factor that out as 1/2, and then the square root of radical 2 plus 2. So what we're seeing here is if I'm on the unit circle, okay, we know on the unit circle that this point is 0, 1. This point at 60 degrees is 1/2 radical 3 over 2. This one is at 45 of radical 2 over 2, comma radical 2 over 2. At 30, we have radical 3 over 2, 1/2. But now remember, with the sum and differences, we were able to find that angle there at 15 and that angle there at 75. And off the top of my head, don't remember what those were. There's radical 2 plus radical 6 over 4 and radical 2 minus radical 6 over 4. But what we're doing now is that there is an angle right there of 22.5 degrees, and the ordered pair for that angle right there, where theta is 22.5 degrees, is now the cosine is 1/2 radical 2 plus 2 underneath that square root here. And then the y value would be square root of 2 minus 2? Yeah, 2 minus radical 2. So it'd be 1/2 the square root of 2 minus radical 2. That is now the ordered pair for that point right there. And now if I wanted to go to, this angle over here, okay, so 180 minus 22.5, it's going to be the same ordered pair, but the x value is going to be negative, right? If I want to go to like 202.5, which would be in this quadrant, it's the same as these two ordered pairs, except they're both negative. And if I want to go to negative 22.5, or 360 minus 22.5, which would be right here, it's the same two coordinates, the y value would be negative, right? Okay. But we can do that with any angle measurement that we want, okay? If I did this with, let's say I want to find the sine of 30, but all I can remember are what these ordered pairs are for 60. Well, I can now use this half angle formula using the knowledge I know about the angle of 60 to give me everything I need to know about the angle of 30 then. Does that make sense? All right. Some of these formulas, guys, are the purpose of them that you're going to see the direct purpose or the direct usage of them. You'll see when you start working in in calculus using trigonometry. Okay, you might take a derivative, or you might have to take an integral in which you have to transform the original problem, because taking the derivative of maybe sine of alpha over 2 is difficult, but you can change that into now the square root of 1 minus cosine of alpha divided by 2. That might be easier, or vice versa. Okay, so it allows you to make substitutions inside those integration and differentiation processes in calculus. The tangent, can not spend a whole lot of time on this, but the tangent, you basically take that one, you're going to divide it by that one. Okay? And through multiplication, so if we did that, I think we might have time. Let's just kind of look at this real quick. If I go 1 minus cosine u over 2, and divide that then by 1 plus cosine u over 2. Because they're both, so the numerator and denominator are under their own radical, can I really do this? Can I put them over or under the same radical? I kind of work backwards that way. Does that make sense? Now you got a fraction times a fraction, right? Can you multiply this times that, but the reciprocal of this times that? So that's going to give me, 2 over 1 plus cosine of u. Those cancel, right? Okay. So I'm going to come down here and do the work. I got now the square root of 1 minus cosine of u over 1 plus cosine of u. Okay. What we end up doing here is we can multiply this by the conjugate, 1 minus cosine u and 1 minus cosine of u. If I do that, up top I get 1 minus 2 cosine u plus cosine squared u, and on the bottom I get 1 minus cosine squared u, right? All underneath the radical. And actually, let's not even do that to the top. Maybe kind of silly to do that to the top. Let's just rewrite. If I multiply these together, can I rewrite the top as 1 minus cosine u squared like that? I'll show you why that maybe makes a better. Sometimes it's more convenient not to actually do the foiling, so you can see a relationship that exists. What is 1 minus cosine squared the same as? Sine squared. So we make that substitution. So we got sine squared u. Now if they're all underneath the same square root, can I put them under their own square root? So I can do that, right? And this is why it makes sense not to multiply these two out on the numerator, because what's going to happen with that square root and that power of 2? Cancel out. And that leaves you with that numerator right there, correct? What happens with this square root and that power of 2? Cancels out, leaves you with that denominator there, right? So now, does anybody have a guess on maybe how they get this version? What do we multiply by here? We multiply by the conjugate of the denominator, right? If I multiply by the conjugate of the numerator, you're going to get that, which, just depending on what you like to do, doesn't really matter. I mean, either one of these is fine to use. Doesn't matter. I don't know that there's any application in which this one would be better. It's choosing that one. All right. Okay, so I want to spend the rest of the time addressing example 4 and then a variation of example 4. Okay, so it says evaluate sine of 2 theta where cosine is equal to negative 2/5, and we know that we're in quadrant 2. This is very similar to, and if we go back to, and we tried to show this the other day, we go back to chapter 5, chapter 6, when it says, if I give you, cosine of theta is 1/2, or 24/25, or something like that, and I ask you, can you then find the sine of theta? Can you find the cosine of theta? Can you find the secant, the tangent, the cotangent, the cosecant? Can you find all 6 trigonometric functions given one trigonometric function, right? Okay. This is the same thing. Now, I'm not asking you to find the other 6 trig functions. We need to, okay, or that'll be a procedure in this problem, but they're asking, okay, if you know what cosine is, of theta, that should tell you everything you need to know to find sine of 2 theta. Just like if I know cosine of theta, that's everything I need to know to find sine of theta, secant theta, cosecant theta, cotangent theta. So we're going to use kind of an approach similar to what we've been doing. Okay? If you remember, if you go back to the first time we saw one of these questions in chapter 5 or 6, I told you that the theme of this question is going to be pervasive through the rest of the course. And this is another situation where that theme type of question shows up. Okay? So as we have theta being a second quadrant angle. So I'm just going to draw my picture. Okay? theta is going to stop in the second quadrant. So there's my terminal ray. Okay. I'm going to draw my right triangle like we always do. Okay. Now it says cosine is negative 2/5. I know that's hard to see on the board, but it's a negative 2/5. So cosine is adjacent divided by hypotenuse, right? So the hypotenuse is going to be 5. The adjacent side is going to be negative 2, right? Remember doing this in other problems. Okay. What is this distance right here going to be? Pythagorean theorem tells us it should be radical 21. If I go a squared plus negative 2 squared equals 5 squared, solve that for a, you get radical 21. Is that doable? Okay. Now, previously, I'd ask you, what is sine of theta? Well, you tell me sine of theta is radical 21/5. If I ask you what's cotangent, you would tell me it'd be negative 2 over radical 21. Okay. So you could tell me all the other 6 trig functions, right? Because you knew what their formulas were. You knew that sine was y over r. You knew that tangent was y over x. Well, now we just extend that a little bit further. We know, and I'm not saying you need to go from memory right now with this because it's something that we haven't spent a whole lot of time on. But my hope is that you say, okay, I know that even though it might not be at the forefront of my mind, I know we've seen this before, 2 theta. Can I reference back to my notes, my textbook, whatever, to realize what that formula should look like? And what it does is this right here. Generates that. Sine of 2 theta is the same thing as 2 sine theta cosine theta. Okay. Well, let's look at our picture. Do we know sine of theta? Do we know this right here? From our picture, it's radical 21 over 5, right? Do we know cosine theta? Negative 2 over 5. And we got this 2 out in front. Okay? So I don't know anything about this 2 theta angle. But if I want to know something about it, I can learn all I need to know about it if I know stuff about the 1 theta angle, which we do. We have that information. So this turns into being negative 4 radical 21 over 25. Okay? So what that means is the y value is a negative 4 radical 21 over 25, okay, when we have this circle that has a radius of 5 units. Okay, now, humor me here. Help me out with this. And let's just kind of draw connections between what we have here and hopefully what logically makes sense. Before we did this problem at all, you knew how many degrees was right there. How many degrees is that right there? 90. Okay. You also knew that this was how many degrees? 180. Okay. Now, that means to us that if I'm going to find so theta is falling between 90 and 180, right? We agree with that? Because it had to be a second quadrant. So that means to us then 2 theta has to fall between what 2 numbers? 180 and 360, right? If I double that number, I get 180 as the kind of the minimum value that I could have for my 2 theta. If I double that number, that's the maximum value that 2 theta could be, right? What quadrants does that put me in? 3rd quadrant or 4th quadrant? What is the y value in the 3rd quadrant or 4th quadrant? Negative. So that negative should make sense, right? Okay. Now, here's my next question. And this might be a little bit more abstract to think about. Those 2 numbers are different, yes? If they were the same, what kind of triangle would that have been? It'd be isosceles, and it'd be a right isosceles, right? If it's a right isosceles, what's another term that we use for that? 45, 45, 90. If it's a 45, 45, 90, that hypotenuse would be traveling through what angle measurement? So if this was a 45-degree angle, wouldn't this have to be going through 135? Okay. So if it was isosceles, if those two blue numbers were the same, we'd be going through 135. So that means then, if I double 135, that gets me to 270, right? Okay. If if our hypotenuse stopped prior to 135, then that means when I double it, my double angle is not going to pass 270, right? Does that make sense? Okay. If I was beyond 135, if theta stopped or terminated beyond 135, that means when I double that, I would be beyond 270 and I'd be into the fourth quadrant. Okay. Now, here's my question. Which one of these numbers is bigger? Radical 21 or 2? Radical 21. Okay. So that means this y value is longer than this x value, which would mean to me that should really stop short of 135, right? So my angle right now, it's not now saying that we're between 90 and 180. I now know for certain, based on these values, that my angle is between 90 and 135. So if I double those two, then my result, my double angle, should fall in this quadrant here, because that's double 135, I get 270, double 90, I get 180, right? And I'm just doing that stuff to give me an idea of how I can check my work here, okay? Let's go through and check our work. When they tell us this, when they tell me that right there, that cosine of theta equals negative 2/5, if I have knowledge about my inverse functions and how I can use my calculator to generate theta, they are hiding theta to me. I don't know what angle, when I start this problem, I don't know what angle they want. If I use my calculator, I can get that angle, right? So let's try that real quick. Let's take our calculators. I'm just use Desmos. I think it's a little bit cleaner on Desmos than it is in GeoGebra. So if we say that they say cosine of theta equals negative 2/5. So that means if I take the inverse of negative 2/5, that should be my theta. Now that's in radians, so let's put it in degrees. I get that. And that's what we anticipated, right? They said it had to be a second quadrant angle. Okay? And we also now are seeing that 113, is that less than the 135 that we anticipated? Okay. So now if they want things about 2 theta, so I'm just going to call that T. Just going to get Desmos to multiply that easily for me. That's 2 theta, right? So if I've got the specific angle now that they're talking about for 2 theta, I should be able to say sine of 2t and get that number right there. Does that make sense? That's the y value when I trace out on this circle 227.15 degrees. Well, we found the exact value to be negative 4 square root of 21 divided by 25. Are they the same thing? Yes. Okay. So that's kind of how you can, one, justify the negative or positive aspect of your answer, and then also justify the complete answer through the use of your inverse functions. Okay. We can do the same thing with half angles. Okay. So let's say we have the same situation. We'll use the same exact information. Let's say we want to find the sine of u over 2 if we know that the cosine of u is equal to negative 2/5. And we're in quadrant 2. So same exact information, same picture. So we'd be looking at, this was negative 2, this was radical 21, this was 5. And that would be, I guess using u would be u. Does that make sense? Okay? So if I want to find a sine of u over 2, okay, it's going to be plus or minus. The numerators for your half angles are the same. They're either 1 plus cosine u. So we've got an option here. It's one of these. Terrible. It's either the 1 plus the cosine of u over 2, or 1 minus cosine of u over 2. The way I remember it is sine has an n in it, and the word negative starts with an n as well. So that's how I remember which one's which. Okay. So all we got to do then is plug that information in. Well, if I'm looking at sine of u over 2, okay, we're going to go, because the sine is this u over 2 is going to stop in what quadrant? Or what quadrants are possibilities? If u stops between 90 and 180, then u over 2 is going to stop halfway between those two, right? Does that kind of make sense? I don't want to say halfway between, but if I cut those in half, between 90 and 45. So I know my u over 2 is going to be in that region right there. So it's going to be a positive y value. So I can get rid of that. So now I'm going to go square root of 1 minus, so cosine of u is negative 2/5, right? All over 2. So I get square root, that's going to be 1 plus 2/5, which is 7/5, all over 2. 7/5 divided by 2 turns into 7/10. So now, if we look at the same concept we did here, instead of taking t and doubling it, let's take t and halve it. Does that angle fall between 90 and 45 like we thought it would? Yep. And then if I go t over 2 here, I get 0.83, so that's the exact y value, okay, at 56.7. If I go square root of 7 over 10, same y value, right? So this is the decimal version. That's the exact version. That's the exact version. You see kind of a purpose of those. I don't know that you see maybe a direct, like, real-life application, but the purpose of our half-angle formulas and our double-angle formulas are to learn something about angles that are bigger or smaller based off of the angles that we already know from the unit circle, okay, or from information that is being given to us, like here, cosine theta equal negative 2/5. As we move on tomorrow, I'm going to skip. We got some other formulas here. They are very marginal formulas, meaning that they don't get utilized very often. Okay. So just for time constraints right now, I want to skip them. If we end up getting through the things that I want to get through, we'll come back and do these. But I want to get the trigonometric equations with you. And so we'll start that. We'll do some examples with our double angles and half angles again tomorrow. But then that will segue into working with trigonometric equations, which is what all this stuff's kind of being built towards. Okay, so we'll start that tomorrow. I opened